Hey everyone, and welcome to The Explainer. Today we're looking at what might, at first glance, just seem like a standard grade 9 science practice test. But I actually don't want you to think of this as an exam. Instead, think of it as a fascinating user's guide to the foundational rules of our universe. We are going to decode the physics and chemistry that govern literally everything you see, touch, and experience every single day.
Okay, let's dive right into this with a foundational question straight from the source material. Imagine the physical stuff around you. Which state of matter has a fixed volume, meaning it takes up a specific amount of space, but absolutely no fixed shape of its own? Is it a solid, a liquid, a gas, or plasma? Think about it for a sec before we reveal the answer.
To get there, here's a quick roadmap for today's explainer. 1. The states of matter. 2. Mixtures and solutions. 3. The math of motion. And 4. Forces, inertia, and momentum. All right, let's kick things off with Section 1, the states of matter. So, returning to that opening question, the answer is a liquid. This is something we experience every single time we pour a glass of water. Liquids have a definite fixed volume, like a liter of water is always going to be a liter of water, but they are highly adaptable. They instantly surrender their shape to match whatever container you pour them into. Solids are rigid, gases expand to fill a whole room, but liquids, they sit right there in that fascinating middle ground. But here's the thing. Matter isn't just stuck in one state. It shifts based on temperature, which brings us to two great concepts from the source material. First, measuring that temperature. To convert our everyday 27 degrees Celsius into the scientific Kelvin scale, we just add 273. So 27 degrees Celsius is a nice round 300 Kelvin. Second, when matter heats up, it usually melts into a liquid and then boils into a gas, right? But sometimes, a solid skips the liquid phase entirely and turns straight into a gas. That almost magical-seeming process is called sublimation.
So what happens when we start mixing them all together? Let's explore that in Section 2, Mixtures and Solutions.
Here's a question to challenge you. Which of the following is a heterogeneous mixture? Your options are salt and water, air, sugar and water, or chalk powder and water. The key word here is heterogeneous, which comes from Greek roots meaning different kinds. Basically, we're looking for a mixture where the parts don't perfectly blend into one uniform substance.
So the crucial point here is that the answer is chalk powder in water. Unlike salt or sugar, which dissolve completely and form a uniform, homogeneous solution, chalk powder is stubborn. It remains suspended in the water, visibly contrasting with the liquid around it. You can literally still see the separate, distinct parts.
Now, the source pushes this concept further by asking us to differentiate between a true solution and a colloid. Notice how it all really comes down to particle size. In a true solution, like salt water, the particles are so incredibly tiny that light passes right through. But in a colloid, think of milk or fog, the particles are just large enough to scatter a beam of light as it passes through. And that beautiful scattering of light, where you can actually see the beam itself, is called the Tyndall effect. Before we leave chemistry behind, let's look at the math of solutions. Imagine you have 40 grams of salt dissolved in 360 grams of water. How do you find the mass by mass percentage? Well, it's just a simple proportional ratio. You take the mass of the salt, so 40 grams, and divide it by the total mass of the entire solution. That's 40 grams of salt plus 360 grams of water, which gives us a total of 400 grams. 40 divided by 400, that gives you 10%. It's an absolutely brilliant, practical way to quantify exactly what's in the liquids we interact with every single day.
And that brings us to Section 3, the math of motion. Motion always leaves a mathematical trail. We're asked, what does the slope of a velocity time graph represent? Well, if you plot how fast you're going against how much time has passed, the steepness, or the slope of that line, tells you your rate of change in velocity. In physics, any change in velocity over time is defined as acceleration. So a steep upward slope just means you're accelerating quickly.
Let's put a real-world engine into that concept. Imagine you're in a car sitting at a red light. You start from rest, so your initial velocity is 0. The light turns green, you hit the gas, and 5 seconds later, your final velocity is 20 meters per second. So what was your acceleration? Well, your velocity changed by 20 meters per second over the course of 5 seconds. 20 divided by 5 equals an acceleration of 4 meters per second squared. See? You just mathematically narrated a real-world driving experience.
Now this brings us to deriving the second equation of motion, S equals ut plus 1/2 at squared. Okay, I know, that looks like a scary alphabet soup, but it's really a gentle logical progression. S is simply the distance you traveled. To find it, you calculate the distance you would have covered if you never sped up. That's your initial velocity u times time t. Then you just add the extra distance you covered because you were hitting the gas. That's the 1/2 times acceleration times time squared. It proves that physics equations aren't magic. They're just an inevitable chain of logical truths about how our world works.
Which brings us to our final section, Section 4, Forces, Inertia, and Momentum.
Look, you simply can't talk about motion without talking about Sir Isaac Newton. We're asked to state Newton's first law of motion, and it is beautifully simple. An object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an external force. Basically, things are inherently lazy. They just want to keep doing exactly what they're already doing. This is the baseline rule for how the entire physical world behaves, and this brilliantly illustrates the concept of inertia. Inertia is exactly that laziness. It's an object's inherent property to resist any change to its state of motion. And how is it related to mass? Directly. The heavier an object is, meaning the more mass it has, the more inertia it possesses. Think about it. It's super easy to stop a rolling tennis ball, but it takes a massive external force to stop a rolling boulder. But when that mass is actually on the move, it has momentum. We're asked for the standard SI unit of momentum. To find it, you literally just look at the formula. Momentum equals mass times velocity. Mass is measured in kilograms. Velocity is measured in meters per second. So you just multiply the units together to get kilograms times meters per second. The math perfectly builds the unit of measurement for you. Let's dramatize that momentum a bit. Imagine a 10-gram bullet is fired from a 3-kilogram gun at 150 meters per second. Because of the rules of momentum, the total momentum before firing, which is 0, absolutely must equal the total momentum after firing. The tiny bullet gets a massive forward velocity, creating forward momentum, so to keep the total universe balanced at 0, the much heavier gun must experience a backward velocity. Because the gun is 300 times heavier than the bullet, its backward recoil speed is much slower, specifically 0.5 meter per second backward, but it is an absolute inevitability of physics. Finally, we are asked to state the law of conservation of mass. It states that mass is neither created nor destroyed in a chemical reaction. And you know, that leaves us with a pretty profound thought to wrap up this explainer. If the matter that makes up everything around us is never created or destroyed, it means every single atom in your body, every particle in the device you're watching this on, has been here since the dawn of the universe. It's just constantly breaking apart, mixing and recombining. So the next time you look at a simple chemical reaction, ask yourself, if it never disappears, what is it going to transform into next? Thanks for joining me on this journey through matter and motion, and definitely keep asking questions about the rules of our universe.